This is the first F for principal component analysis for helping you to understand principal component analysis. And it shows simply main principles. First of all, what latent variable is, what projections on latent variables are, and how this latent variable should look like in order to call it a principal component. So let's start with the data set. So you can see that we have a very simple case with two variables, x1 and x2. You can see these variables in the values for these variables in this table, the first two columns of this table. The last row in this table, it's a sum of all these values. So you can see that sum of the x1 and x2 is 0. It means that average is also 0. Because as you can see here, we mean center the data. So if you don't mean center the data, if you click no here, you can see that the average will be approximately 2.62 here and 2.03 here. Okay. Let's continue with centered data. So the blue points represent the original data set. So for example, if I click on this point, you can see that the blue point has coordinate 1 and 0.3, and then you can see that this is 1. You can see the scale here, and this is indeed 0.3. Okay. The orange line, it's the latent variable. So you can see that you can also rotate the latent variable. I call it PC, although it's not always PC. It should meet a certain requirement to call it PC. You can see you can rotate it. This is just the angle in radians. And then you can see that all blue points are being projected to the orange line, right? So you can see, for example, this point has a projection here. And projection is simply, you can see it simply, you can kind of fall this point to a line. So the angle here is 90 degrees. This is the distance between the projected point and the original one. Okay. And then you can see that depending on the angle, I can have different spread of the orange points. For example, in this case, the spread is the smallest. And in this case, the spread is almost the largest in this case, right? So the overall idea is we can measure how much of this spread we can actually capture. So how close the orange points or the spread of the orange points will be to the spread of the blue points. And you remember from statistics, we measure spread using variance, where variance is simply an average squared distance between the points and the mean. Luckily, the mean here is 0, so the mean of x1 is 0, the mean x2 is 0. It means that the center point of the data cloud is exactly in the origin. So if we want to find a variance, we need to find squared distances between every point and the origin, and that distance is given by this blue line. You can calculate this distance remembering that the x1 and x2 coordinates of every point form a rectangular triangle. So it means that this distance between the origin and the point is simply a sum of squared coordinates, right? So that's what we call a Euclidean distance. So this is hypotenuse and these are two cathetas. You can see it here, right? So the calculation. So if we take x1 coordinate, square it, x2 coordinate, square it, so this will be approximately 0.81. This will be approximately 0.36, and then together it gives you 1.18. So this 1.18, it's a squared distance. It's the square of this length of this line. Right? Then you can calculate, of course, it for every point here. And then if you take a sum of all squared distances, so this will be a sum of squared distances. You can compute variance if you divide to n-1 to 9. So that will be the variance of these blue points. Okay, but we don't need the variance. We just need a sum of squared distances because it has a direct relationship to the variance, right? And then you can see this is the sum of squares. So this is the spread of the blue points. Okay. Now how to measure the spread of the orange points? Well, the orange points have only one coordinate, right? So it's a position of this orange point along this orange line. So for example, how far this, or let me just select this one, how far this orange point from this origin. So this position, the distance between the orange point and the origin along this latent variable, we call it a score in PCA. And score is simply a column that you see here. So it's simply a distance between the projected point and the origin along latent variable. That's what we call a score. So apparently if we square the score, and then if we take a sum of squared scores, we will get a variance, a spread of the orange points. And that's what you see here. So this is the scores. So for example, you can see this is 0.81. If we square this value and round it to 2 decimals, we will get 0.66. So this is a squared distance between the orange point and the origin. And this is what we, if we take a sum of squared distances, this is what we get. So this is a spread of variance if you divide it to n-1 of the orange points. And then you can see, for example, in this case, the spread of the orange points, it's 2.13, sum of squared distances. And sum of squared distances for blue points, it's 4.39. So this is almost a half of this, right? So it means that if we take orientation of our latent variable like it's shown here, we can explain only a half, or the points when they are projected to the orange line, to this latent variable, the spread of these points is almost a half of the spread of the original points. And this is information also is given here. Sum of squared distances for blue points, 4.39, this one, right? Sum of squared distances for the orange points, 2.13. You can see 2.13 here. And this is the percentage. So how big this value in relation to this one. So you can see it's almost 50%. We also have the third distance, right? So again, if I select any point here, for example, this one. So this is a full distance squared, full squared distance. This is the distance that we can explain by projecting the point to the latent variable. And the distance between these 2 points, between the original point and the projected point, it's called residual distance, right? Apparently, you can see that these 4 distances, because they are squared, they form a rectangular triangle. So it means it's a squared full distance. It's a sum of squared score distance and squared residual distance, right? And then when we rotate the orientation, if we change orientation of the latent variable, you can see we change the ratio between this distance and this distance, while the full distance remained the same, squared distance remained the same, right? And the idea is that we need to find an orientation of latent variable which maximizes the explained distance and minimizes the residual distance. And if we find the minimum for residual distance and maximum for the explained distance, we will call this latent variable as principal component. So principal component is a latent variable which maximizes the spread of the projected points in relation to the original spread, right? So let's try to find such position by manually. So you can see, for example, in this case, the residual distance is 4.11, the explained distance is 95.9. So if I change it and try to minimize it, you can see 4.9, 4.09, 4.05, and you can see it goes up again, right? So we definitely have a minimum approximately here, right? So you can see like this. So probably this is the most optimal position because it gives, at least if I do it manually, it gives the maximum spread of the orange points and smallest residual distance, sum of squared residual distance, right? You can also do it automatically. There are several algorithms. For example, Next Up explains one of these algorithms. If you click a point fit, you can see that I got even smaller, right? It's 4.04 here. So I couldn't do it manually, but if I use an algorithm which fits the orientation automatically, then you can see the residual distance even smaller. Okay. So this is exactly how PCA and many similar methods work. So we have a latent variable, we have projected points, we have a spread variance of the projected points, we have spread variance of the original points, and then we have the residual variance, right? And for example, in PCA, we try to find orientation of principal component that minimizes the spread of that minimizes the sum of squared residual distances or maximizes the spread of the orange points of the projected points. Okay. And then you can see the last column here, it represents the residual distance, the gray one, right? For example, in this case, you can see this is this squared plus this squared, right? So if you select any point, you can see the blue line, it's this distance, the squared length of blue line is this value, the squared length of the orange line is this value, and then finally the squared length of this line, of the gray line, it's this value. So the sum of squared residual distance and score distance gives you the full distance, the original distance. Okay. And then finally, how this orientation is defined. It's defined using a special thing which is called a unit vector. So we have a vector. You can see this is called P. We call it loading vector. The length of this vector is 1, and then you can see this is x1 portion of this vector, and this is x2 portion of this vector. Again, what does it mean? It means that if you make a triangle, for example, let me just select any position like this. If you make a triangle So the length of this, the hypotenuse of this triangle will be 1, and this hypothesis will lie exactly on this latent variable. Then this cathetus, the x1 portion, will be 0.8, and this portion will be 0.61, as it is shown now here on this sketch. Okay, so this is the overall idea: latent variables, distances, variances, and in case of principal component analysis, principal component, it's latent variable oriented to maximize the variance of the projected points or minimizes the variance of the residual variance, the distances, the squared distances between the original points and the projected points. Okay. So, and then one more thing, you can, first of all, you can play and take different samples and then feed them, different samples and then feed them, and then you can see that this percentage, of course, it will depend on the sample. But in PCA, we almost always center the data, so to get the average equal to 0, because if you don't center the data, then it will be difficult to catch the maximum spread. For example, in this case, you can see that the component is oriented along the spread, but you can see that the residual distance is very large and the explained distance is quite small, right? And then you can, if you try to do it better like this, you can see indeed this distance is smaller, but you do not capture the direction of the points, right? So you can see the direction of the points is approximately here, but we cannot capture it because latent variable, like any other variables in the space, they start in the origin. And if they start in the origin, we cannot capture this direction. So we need to center data and then fit, and then you can see now we indeed capture the direction very nicely.